this kind of builds to the bigger picture where, just like in the invention of a blockchain, it wasn't enough to just build a proof of work or proof of stake or Merkle trees to the solution. You needed a set of technologies. The same thing here. If you want to build a privacy-preserving blockchain that is like the best, then it's not enough to use a single tool. You actually need to use a toolkit. And the goal of Secret 2.0 is basically to take the most common classes of solutions in the literature from the past, like let's say 40 years, and compose them together in a way that kind of builds the best privacy tech stack. And on a very high level, just so people kind of get the basics of why you can't use a single solution. So we already touched zero knowledge proofs. We already said that if you have more than one user, then you gotta trust some data manager to see all the data, which is not a desired situation. And then when you use trusted execution environments, which everyone knows is what Secret currently uses today, then I do still think that for many use cases it's fine. But if you have like more higher sensitivity data, or like you're okay with maybe taking a performance degradation, then you would actually want to probably combine that technology with other cryptographic building blocks like MPC and FHE and zero knowledge proofs. Now the question, okay, zero knowledge proofs alone, they're not perfect for these. T's maybe not perfect for these. I would argue they're better for the general computation, but still not perfect. So there's this crazy tool set called MPC, which stands for multi-party computation, and FHE, which stands for fully homomorphic encryption. It's kind of nice that all of these acronyms are three-word acronyms. I don't know if this is intentional or not, but anyway, with MPC and FHE, and I'm talking about a specific part of FHE, which is threshold FHE. At the end of the day, the trust model is that you don't need to trust like a single entity, like in the zero knowledge proof situation, but you do have to trust a network. So this is very similar to how a blockchain works. In a blockchain, you trust that the majority of the validators don't collude. And in MPC and FHE, you basically need to trust that, again, the majority of validators don't collude here as well. But there's a very distinct difference, and this is why we trust blockchains to work, and we can trust MPC FHE as it is. You can trust MPC and FHE as it is, because at the end of the day, the attack vector is much simpler. In blockchain, like let's say in Cosmos, if 1/3 of the validators don't produce blocks, then the chain halts, and it's very easy to see who produced blocks and who didn't. So there's accountability, there's actions you can take. The system also breaks explicitly. With privacy, that's not the case. What happens is that those validators, they can just go off-chain, they can open a Telegram group, and they can just share their keys or their shares of their keys together, and they can de-anonymize and break the encryption of the entire network, and no one would know. There's no repercussions, there's no accountability, and it's very simple. And for that reason alone, combining MPC and FHE with T's that's probably the winning solution. And you also need zero knowledge proofs a bit, but the main components are T's combined with MPC and FHE, because T's make it very, very hard, extremely hard, to extract data from the enclave. Now you've just made it exponentially harder to break like the majority of validators in the network. They can't just open a Telegram group and share their data in the clear. Now, MPC is very broad, FHE is very broad, but the way we kind of envision this is in kind of two angles. So we envision this on the bottom-up angle, and that is the MPC angle. So instead of building general compute MPC, then what we're actually gonna do is we're gonna start to add like the lowest hanging fruit, the kind of like specific MPC technologies into Secret that actually enable the most use cases with the highest level of security and the highest level of performance. And that is actually something that, and we actually researched this a lot, and we realized that specific set, first frontier, first set of technologies is threshold cryptography. I actually envision the threshold cryptography specifically is gonna become a big deal in many of the blockchains. And I think Secret's goal should be to, kind of spearhead that effort in its own. Now, threshold cryptography basically does a simple thing. It allows, it only focuses on signatures, like signing transactions, and encryption, decryption, right? And when it comes to encryption, decryption, signing and signing, then the idea is that anyone can verify signature, that's still public. Everyone can encrypt data, that's still public. But the private key itself, the decryption that uses the private key, or the signing that uses the private key, that's done in a distributed manner. So the keys are split across all of the validators. That is the MPC part. And then the key is never reassembled in a single place. You can produce signatures, you can produce decrypted values without actually creating a single point of failure. Now, when it comes to, let me give you a concrete example, because this may not be very clear from the get-go, but let's take private voting. You can do private voting on Secret today, and we've done it. But if you want to hear about a hardened version that uses cryptography plus T's, then the way it's going to work is as follows. You're going to write a private voting contract, and it's going to look the same. If you've ever seen a secret contract, it's going to look very much the same. But that contract on the back end would essentially initialize a new key pair, a private key and a public key, but the private key would be shared by all of the validators, as mentioned, and it never would exist in one place. And our users, as usual, they know the public key, so they can encrypt their votes, and the vote should be 1 and 0. Say like 1 if they're voting for a specific contender or applicant, and 0 otherwise. And here is where you actually use zero knowledge proofs, because users, if you don't use zero knowledge proofs here, then users can arbitrarily cheat, right? They can encrypt a value of like 10 or minus 15, and you would never know. So this is an example where zero knowledge have to be integrated and are very effective, but they're just part of the solution. And then validators can just tally the votes as usual, because the encryption scheme is not a regular encryption scheme, it's a homomorphic encryption scheme. So this would actually work with the underlying cryptography changes, but from a developer point of view, this would look like the same voting contract that you see today. And at the time of revealing the vote, when the vote is done, then the validators can participate in threshold decryption protocol, where essentially they just decrypt the result of the computation, which gives you the end result, like each candidate, how many votes they got. And the important part is that you see it's the same user experience that we have in Secret 1.0, but this already combines MPC, zero knowledge proofs, homomorphic encryptions, NTs, all in one, to create a much better and much more robust system. And the goal is really to expand way, way beyond that. I'm done with the very technical piece, and now I'm going zooming out and going high level again. But the point is that, we're going to build all of these into Secret as well, but we also believe in this idea that's very natural for Cosmos, where you, instead of having like a single chain, over time, Secret would actually horizontally expand to a constellation of chains model. Now, these chains are going to be tightly integrated with each other in ways that benefit both, and Secret would be the gravitational center of all of these. So, for example, we're looking into a fully homomorphic encryption chain, and that chain would probably have some kind of interchain security-like model between Secret and that other chain. And there are many, many other chains that we can think about. Some of them can be developed internally. Some of them can be supported internally by Secret Labs, by others. And many of them can actually be completely external. I think the only stickiness that needs to be important in the constellation is to make sure that any constellation chain shares the same privacy, private compute values, privacy mission that Secret shares. And now the last part that I want to talk about is what does this mean for tokenomics? And I really think that we came up with something that would actually have been much more optimal. Like if we were designing Secret from today from the get-go, this is what we would do. That's the idea. And the key features for what we came up with, and this is not my own word, this is like, again, I can't thank enough the dozens of people in the community who've commented and worked on this. But the main properties of this is that we wanna enable growth. And the way to enable growth is by setting up domain-specific funds that propel that growth, that kind of, let's say, help Secret grow in the places where it had the most trouble growing. And then the others idea are that it doesn't matter what we do short term, within like a few years, inflation is gonna decrease, and it's gonna decrease not rapidly but gradually to make sure that this is something that is easy for everyone to get used to. But at the same time, it's been done in a way that, which in my opinion is really important, that makes sure that stakers are always ROI positive, which means that they're never diluted by inflation. They always continue to outpace inflation in any year, even year one, even year two, short term, long term.